Hi Markus. Yeah. We don't share as he has a person who has co-host, maybe should be fine and shouldn't be able to share. Okay. That's true. Thank you. And use the microphone as well. In order to. Are you this one? Yes, teacher. Just it's because the only way that the some people can hear us.
Yeah.
Hello.
No need.
It's got for the Zoom and I produce for the speakers. It's just for here to make it listening. I don't hear.
I think
Marcus, you can start.
Okay, can you hear me?
Yeah, we can hear you. You can start.
Okay, nice. So I can start? Okay, I will begin. Hello, my name is Marcus and welcome to my talk titled Empirical Linkage Learning Provably Builds Truthful Models on Concatenated Traps and Hierarchical If and Only If. This is joint work together with Dirk Sudholt. Okay, what is our problem? We want to find the global maximum of a pseudo-Boolean function. And we have the following idea. We acquire problem knowledge, in our case linkage, during the run of the algorithm and use it to hopefully boost performance. So now what's linkage? Intuitively, linkage is defined as dependency between decision variables xi and xj, where xi and xj are dependent if they're part of the same subproblem. Note that knowing linkages may be of intrinsic value. Okay, let's do an example. We define concatenated traps as the sum of n divided by k disjoint traps of size k. So we take n bits and divide them into n divided by k blocks of size k. And in every block, we define a trap, which you can see here. On the x-axis, there is the number of ones, and on the y-axis, there is the fitness. We have a global optimum at the all one string and a local optimum on the all zero string, and the fitness decreases as the number of ones increases. And in this case, two decision variables are dependent if and only if they are part of the same trap. Then how can we represent linkage? We can use a matrix with non-negative entries where 0 stands for there is no linkage, to the best of our knowledge at least. We can represent higher order linkage by using subsets of the power sets of the set of bits, and we call F a linkage tree if F is a binary tree. Here you can see an example. Note that an inner node is the union of its children, and the leaves partition the root. That is the set of problem variables, the set of bits. Okay, we can generalize this notion by not considering a linkage tree, but a linkage forest, which is a set of disjoint linkage trees. Here you can see an example. I only removed 2 nodes from the previous example, and now we get the linkage forest. How can we build a linkage forest? Typically, one starts with the set of singletons and iteratively merges 2 bit sets U1 and U2, which maximize this similarity measure, which is the average amount of linkage between bits in U1 and U2. And some algorithms stop when there are no such U1 and U2 such that this similarity measure is strictly greater than 0. Here we can see an example. In this example, we have 4 options for U1 and U2. This set 1, 2, this set 3, 4, this set 5, 6, 7, and this set 8. And now let's say 1, 2, and 3, 4 maximize the similarity measure, then they are merged in the next step. Here we get the node 1, 2, 3, 4. Okay, there are 3 types of linkage learning. First of all, there is statistical linkage learning, which aims at learning linkages via statistical analysis of this distribution of patterns in a population. There are at least 3 important algorithms: the gene pool optimal mixing evolutionary algorithms, the parameterless population pyramid, and the dependency structure matrix genetic algorithm 2. Then there is empirical linkage learning, which learns linkages via considering difference in fitness of neighboring solutions. Most notably, there are the ELL-based GOMEA and the ELL-based P3. And there is hybrid linkage learning, which combines statistical linkage learning and empirical linkage learning. And most notably, there are the HLL-based GOMEA and HLL-based P3. These types have different pros and cons. SLL linkage learning is cheap in the sense that it doesn't require additional function evaluations, but it may report false linkage. Empirical linkage learning provably does not report false linkage, but needs additional function evaluations to learn linkage. Okay, to the best of our knowledge, there are 2 theoretical analyses of algorithms using linkage learning. First of all, there is the analysis of the SLL-based P3 on concatenated traps and the hierarchical if and only if problem, and the analysis of GOMEA on concatenated traps. But here the authors assume that the correct model is already incorporated into the variation operator. We, in our paper, performed a theoretical analysis of the ELL-based P3 on concatenated traps and the hierarchical if and only if problem. Why is our result contribution useful? First of all, concatenated traps and hierarchical if and only if are relevant for benchmarking. Secondly, we gained insights into population dynamics and model building. And thirdly, we give runtime guarantees for arbitrarily large input sizes n. How does empirical linkage learning work? First of all, we need some notation. We consider a solution x and define delta ix as the fitness change when we flip bit I in x, and delta ij of x as the change in fitness when we flip both bits xi and xj in x. Then we can define the amount of nonlinear interaction between 2 bits xi and xj in x omega ij, which is the absolute difference between delta ij and the sum delta I plus delta j. Note that if we have linear interaction, that is the change in fitness when we flip both bits can be expressed as the change in fitness when we flip bit I plus the change in fitness when we flip bit j, implies that the amount of nonlinear interaction between these 2 bits in x is 0. Okay, then there's a nice theorem which tells us if the amount of nonlinear interaction in between I and j in x is greater than 0, then xi and xj are dependent as defined before. Okay, how does the parameterless population pyramid works? First of all, the P3 computes its population, partitions its population into different sets, let's say gamma I to gamma D. And then a generation of P3 looks as follows. First of all, P3 generates a new solution, Y1, adds it to gamma 1 if not in the population. How is Y1 generated? First of all, P3 chooses a solution from this set of binary bit strings uniformly at random, and then applies a hill climber to this solution in order to generate a local optimum. Then, after generating this new solution, the Y1 climbs the pyramid. So in the if iteration, the following happens. P3 generates a new solution yi plus 1 by crossing yi with elements from the level gamma I by using the elements of our model as crossover masks. If this solution has strictly greater fitness than the parent and is not yet in the population, then it is added to the next layer, that is gamma I plus 1. So now we have to incorporate model building into P3. We did this as follows. We represent the linkage by a matrix M, and the entry Mij of this matrix is the average amount of nonlinear interaction between bits I and j in the population. And then we use this matrix to build a linkage for us according to the algorithm I described before. And we need, in order to do so, we need theta of n squared times the cardinality of gamma function evaluations. So now I have to explain what the hierarchical if and only if problem is. So first of all, we need some definition. We call a solution pure for a set of bit positions if all bits in X indicated by the set have the same value. For example, we consider this solution 1, 1, 1, 1, 0, 0, 1, 1, and which is pure for the set 1, 2, 3, 4, because the first 4 bits are all 1, but it's not pure for 5, 6, 7, since here we have 0, 0, 1. Okay, now we are ready to define the hierarchical if and only if problem, which is defined on a suitable binary tree T with decision variables as leaves, and the h if value is computed for a solution X as follows. We scan T from bottom to top, and if X is pure for node F in T, it contributes its kinetic fitness. Let's do an example. We consider the search point 1, 1, 1, 1, 0, 0, 1, 1. On the left-hand side, we have our ground truth T, and now we evaluate X. Clearly, X is pure for every set of cardinality 1, so each set contributes 1 to fitness. Then we consider sets of cardinality 2, that is, for example, 1, 2. Again, X is pure for 1, 2, so this set contributes 2 to fitness, and so on. The same happens for the set 1, 2, 3, 4, since X is pure for the set, so this set contributes 4. But X is not pure for the set 5, 6, 7, 8, since here we have 2 zeros and here we have 2 1s. Okay, now our contribution in detail. The first table shows the expected runtime of P3 on concatenated traps with trap size X. Here the runtime is defined as the number of function evaluations. So we have an upper bound of O2 to the k times n times the logarithm of n divided by k from a previous work from 2016. And we made this result tight by proving the corresponding lower bound for the SLL case. And in ELL case, we prove for the general case lower bound of omega 2 to the k times n times the logarithm of n divided by k. And then upper bound O2 to the k times n squared times the logarithm of n divided by k. And for the case where k is at least 2 times the logarithm of n, we get a better upper bound of O2 to the k times n times the logarithm of n divided by k. Okay, now we also proved something for the hierarchical if and only if problem. Again, in the work from 2016, there was proven for the SLA case a lower bound of omega n times the logarithm of n, and for the simplified P3, an upper bound of O n of n times the logarithm cubed of n. And we proved for the ELL P3 a lower bound of omega n squared times the logarithm of n, and an upper bound for the simplified P3 of n squared times the logarithm cubed of n. So now I want to talk about model building in more detail. We have the following corollary. We have that the amount of nonlinear interaction between 2 bits I, j in X for the case of hierarchical if and only if. So this is strictly greater than 0 if and only if X is pure for the smallest node in the tree which contains both bits I and j. Let's make an example. We consider search point 1, 1, 1, 1, 0, 0, 1, 1, and flip the third bit from 1 to 0 and the 6th bit from 0 to 1. Here we can see that if we flip the bit 3, this block of size 4 is deactivated, and this block of size 2 is deactivated. And if we flip only bit 6, then only this block of size 2 is deactivated. If we flip both bits, then we deactivate this block of size 4 and these 2 blocks of size 2. And now we can see that the set of deactivated blocks when flipping both bits 3 and 6 is the disjoint union of this, the blocks deactivated when flipping only 3 and 6 separately. And so we have linear interaction. We are not able to find any linkage. Now we consider a different case. We take the same search point 1, 1, 1, 1, 0, 0, 1, 1, but now we flip the bits 2 and 3 from 1 to 0 respectively. So if we flip bit 2, then we lose this block of size 2 and this block of size 4. This similar for when flipping the third bit, we lose this block, and we note that there is an overlapping deactivated block, which is this block of size 4. And if we flip 2 bits together, we lose this block of size 4 and these 2 blocks of size 2. And so since this block is counted twice, we have nonlinear interaction. And now we find linkage. Okay. And now I want to mention that the amount of nonlinear interaction decreases as the distance between 2 bits increases. So for example, consider this graphics. We have 3 bits, I, j, and k. And we see, and I and j are closer together than, for example, I and k, since the smallest block which contains both bits I and j has lesser height than the smallest block which contains I and k. If we flip bits I and j, then we can calculate the amount of nonlinear interaction by considering the deactivated blocks marked in the green area. And similarly for the case where we flip bits I and k. And we see that the big area is a strict subset of the small area, and so this holds intuitively. Okay, we prove the following theorem for model building on hierarchical if and only if. We consider F to be the linkage forest based on any population gamma of P3 on hierarchical if and only if. Then the following holds. Firstly, the model F is the set of all singletons and all blocks for which linkage has been witnessed. What does this mean? Consider the search point 0, 0, 1, 1, 0, 0, 0, and assume that it's in the population. We see that this search point is pure for the last 4 blocks. And we assume now that this thing on the right-hand side is our ground truth. And then the first thing tells us that the set 5, 6, 7, 8 is indeed in the linkage forest. Now consider the second. The model F contains every subtree rooted at any correctly modeled block. What does this mean? Assume that the set 5, 6, 7, 8 is in our model. And the thing on the right-hand side is our ground truth. Then 2 means that the sets 5, 6, 7, 8 are in F, for example. Okay. Now we look into the proof idea. So we consider that this population starts with the set of singletons. We know that the amount of nonlinear interaction decreases as distance between 2 bits increases. So we have no option then to, for example, merge 1 and 2 or 3 or 4. So now we have a problem since this set has cardinality 2. But our second observation says, okay, concrete bits are irrelevant comparing U1 and U2 by clustering. What does this mean? This means that it's enough to restrict attention to 1 bit in this set. So it's enough to compute the amount of nonlinear interaction between bits 1 and 3, for example, or between 1 and 4. And now we can use the first observation, that is that the amount of nonlinear interaction decreases as distance increases. And so we merge, for example, bits 3 and 4, and so on until we generated all sets of cardinality 2. Okay, now we see that we are not able to find linkage between these sets 5, 6, and 7, 8, because there is no solution in population which is pure for the set 5, 6, 7, 8. So there is no other option than to merge these 2 sets, and we get this part of the ground truth. Again, as I said, we cannot generate this since the algorithm has never seen solution, which is pure for the sets 5, 6, 7, 8, and ELL extract the maximal amount of information possible. So to wrap up, what are the takeaway messages? Empirical linkage learning in combination with the linkage forest works on concatenated traps and hierarchical if and only if as intended. In particular, empirical linkage learning extracts maximum amount of information. SLL outperforms ELL on HIF, at least when implemented into P3. And ELL is as good as SLL on concatenated traps if the trap size is at least 2 times the lower of n. Since in both cases we get an expected random of theta 2 to the k times n times the logarithm of n divided by k. So what we do future research is we want to consider Gomea on hierarchical if and only if, and we want to try to reduce the overhead from linkage detection. Of course, this list is not exclusive. Thank you for your attention.
Question. Okay. Is there an online question? You can ask it. Read it here, right? Yeah, if you want to ask a question online, you have to unmute your mic, of course. Otherwise, we have a question here in the room. Yeah. Okay.
Okay, so as far as I understood, so nice talks, first of all, thank you. As far as I understood, the linkage is actually dependent on the actual split string. So does this mean we always have to learn the linkage new? Or I didn't get that in detail. Can you comment on that? So, I mean, the linear interaction depends on the bit string, obviously.
Yeah, right.
And so for hierarchical if, that's probably easy, because it doesn't change, I guess. But
Does not change.
the linear interaction.
But
so
when replacing the bit string.
Sorry?
When replacing the bit string.
Yeah, so when the bit string changes, the linkage between I and j doesn't change, does it? Can it?
Yes, yes. So we have this criterion which says that we are able to detect linkage if and only if X is pure for the smallest element in the ground truth which contains both bits. So this was this example for the solution 1110011, where we are not able to detect any linkage. But if you have if you put in here the all one string, then you're able to detect linkage.
Okay. The presentation was too small to see, but I think I could follow. Okay.
Can I maybe add to this? So in a sense, we're looking to find a witness. So that is a search point that shows us some linkage exists. And then once we know that linkage exists, then we can adapt the model accordingly. And then we know forever that this linkage exists, no matter what other search points we find. So, and what I find fascinating about this linkage learning is that it's kind of a search for witnesses, and witnesses help us to create linkage, and this helps us to evolve better solutions. And those better solutions give us more witnesses because we find better and better and higher blocks. And so this is kind of a dynamic that goes in hand. We've got synergies between evolving good solutions and finding linkage. So that's one thing that's kind of come out of our work.
Okay, I see. Thank you very much.
Okay, and any other question? Michael.
Hi. Thank you for the presentation. Especially thanks for the paper. It's really very good. My question is actually about the future. Do you think you can extend your analysis or your models or propose a new one? Not for hierarchical problems, but for overlapping problems, at least a little bit.
So you mean, for example, concatenated traps with overlaps?
Yeah, like cycling traps, for instance. Yeah.
The model building, I think so. So I'm not sure about the analysis, because for overlapping traps, you cannot prove that P3 has For concatenated traps, the pyramid of P3 has a height at most 2. You cannot prove this for concatenated traps with overlaps. So this is
Okay,
one
but maybe you
obstacle.
can, so you don't, so you cannot extend it that way.
Maybe so. We haven't looked into it, but we will.
You really can, but I will keep the fingers crossed because this may be really, really valuable. Thank you.
Thank you.
Yeah, thank you.
So I'm not Duke here. If anyone wants to have the mic,
I can ask, but. Okay, any last question? All right, let's thank our speaker again then. Thank you, Marcus.
Thank you.
Our second speaker is not online yet, so if you're there, probably not. No? All right, then we have to go to the third speaker, which is not online. And that's a talk about on the use of matching algorithms to transfer solutions for the TSP problem.
Yeah, it's fun, but it's not very. Let me check. So,
yeah, let's just switch with you could just stand there.
yeah, you can like.
Yeah, I think it's
from
nice to do
here.
that. You have to plug in the mic. Yeah, no, that's. Yeah, this is gonna, yeah. Okay. Yeah, it means I'm not gonna be able to point to things easily, but that's all right. Okay, hello everyone. My name is Liam. I'm a first year student at Adelaide University. This is actually my first conference and first presentation, so sorry in advance if the talk's not great. It's on the use of matching algorithms to transfer solutions for the traveling salesman problem. So to begin with as well, this presentation isn't in the format of the paper. It's actually in the presentation of how it was done. Because we didn't actually set out intending to do this paper. We set out kind of intending to solve another problem, and this was just one of the.
This meeting is
And
being
our
recorded.
optimization goal is to minimize the make span, which is the total time it takes for the last agent to finish all its tasks. Traditional methods offer solutions, but struggle to scale, or it's a trade-off between suboptimality and scalability. And the centralized methods are more scalable in nature, but typically ignore global prediction or long-term look ahead. Although prior work in swarm robotics has explored local coordination among the agents to make it more scalable and also applied deep learning methods to estimate the congestion, but none of them has addressed this multi-agent pickup and delivery task at a scale in a decentralized fashion. This is the gap that our work fills. So as you can see in this slide, our proposed method is a kind of hybrid solution that combines decentralized A*-based path planning with local collision detection, which actually includes message exchange among the neighborhood agents, and then using a kind of global congestion prediction as a value to the A** algorithm to also consider the cost of long-term congestions while doing the planning. Local Path Planner module. At the core of the agent's decision-making is an adapted A** search. The cost function includes the congestion cost. This can be learned from global predictions and also the rotation costs that an agent would actually have based on the path that it might take, and which allows the agent to choose paths that are not only short but also less congested. So the heuristics of the A** consider both the shortest path using this Manhattan distance and also the congestion awareness, a long-term prediction, but also the local actions that an agent takes, which depends on how or where the agent must go, the next steps. We consider different conflict types for our proposed method. We address a variety of conflicts, whether it's a node conflict or edge conflict or swap or deadlocks. As you can see in the figure, each of them are defined differently and also explained more in the paper. So I refer the audiences to also have a look into the paper to have more detailed description of these conflicts. So the agents can communicate locally, prevent collisions, which actually helps the scalability. And then each agent would have different priority among the other agents. For instance, the one that has a package to be delivered has more priority in terms of the other agents who are going towards some pickup points. So in our simulation, we actually evaluated different type of scenarios which are reported in the paper. And then the information that is communicated among the agents in the nearby radius is also the planned path. I mean, the 3 next step planned path. So they all know which actions are they going to take in the next 3 time step. And then the agents also would be able to perform different functions like waiting or moving or replanning to avoid local collisions. There is also something that we call wandering mode. So we try to mitigate some of the deadlocks and blocking agents via an operation called wandering. So for instance, if there is some congestion in some specific node, the agent just try to go around and do not cause the conflict to be worse. So we call it a wandering operation. So wandering operation could be activated if job node is blocked somehow or congested, or a maximum temperature is reached, which is actually affected by the agents in the collision area, where there is more congestion or there are more agents in some nodes. It's also affected temperature of the individuals, or all the jobs are already completed. So, as I said, our work is inspired by the work of Yu and Wolf, which considers the static obstacles in a kind of grid-like environment where agents try to find a path towards some destination. but also some long-term prediction using convolutional neural network. So we take inspiration of using this deep neural network to also for map the problem and use this global congestion information as an input to A star. We use actually a grid-like environment with static obstacles and also task nodes. And the agents can plan independently and communicate locally. But then, as I said, there are different operating modes. The agent could be in pickup state or delivery or wandering state. And there are different actions that an agent can take from translation, rotation to waiting. And each of them has some specific cost defined. And we use different colors for different agent mode to use kind of images of the environment that can be processed later on to use the convolutional neural networks for predicting the long-term congestion based on the priorities of the agents. So we save the frames to be processed later on. The congestion model is trained on simulated data and predicts the probability of congestion in the upcoming frames using a multivariate normal distribution adjusted for both spatial and temporal dimensions. So as you can see, we use a convolutional neural network to predict the next time states, and the architecture and the detailed information are already shared in the paper, ready for further readings. And the way we simulate this setup is we consider 10 agents, and we also increase the number of agents to up to 25, and we have 15 by 15 grid size with 10% static obstacles in this grid. And we consider a comparison between the baseline, which does not consider the global congestion information or not taking into account, and with the KPIs for evaluation kind of make span, throughput, and scalability. So the first set of figures evaluates how make a span looks like for different approach for our method and also the baseline. So the figure compares the performance of the baseline method, the top, with our proposed method across 3 different settings, varying the number of agents from 5 to 25. And as you can see, the y-axis represents the number of steps required to complete the task, with lower values indicating the better performance. As we can see, our proposed method consistently outperforms the baseline across all agents configurations. Both methods actually perform similarly for few number of agents, although our method still shows a slightly reduced variability and slightly better median performance. As we increase the number of agents to 10 and then 25, the performance gaps becomes more illustrated. And then this in general demonstrates that our approach is significantly more scalable and robust in multi-agent scenarios, maintaining efficient coordination and task completion, even as the system becomes more complex, I mean, in terms of number of tasks and number of agents. And then the throughput analysis, as we can see with 5 to 10 agents, both methods reach 100 task completion. But when it becomes to more agents, such as 25, the baseline task completion is lower compared to our methods. And our methods outperforms the baseline in terms of the throughput. So as you can see, it's already shown in the bottom figure that our throughput in our methods increases from 38% to 76%. And then to conclude the results, we can see that our congestion-aware method reduced the make span significantly, and also in terms of throughput, it's nearly doubled when we have actually a system that includes the high number of agents. And also it's robust in terms of dense setting, meaning that more tasks and more agents are included in the system. And to conclude and bring some discussion points, I would like to say that in summary, we combine local and global intelligence for efficient multi-agent path planning. And our method scales better than centralized ones, and is robust under realistic conditions. And it's highly adaptable to real-world applications like swarm robotics, warehouse automation, and even traffic control systems. And as the future work, we plan to integrate different learning methods, such as reinforcement learning, and extend our model to non-grid environments or more complex environments. With this, I would like to thank for your attention, and also thank the committee and my co-authors for their contribution. I would be happy to take your questions online or via email.
Okay, thank you very much. Do you have questions?
Is there a question? We're running late. There's no question, but people saw the email address, right? So they can contact you if there are any questions. All right, I will have to close the session here. Thank you very much for the presentation. And
Thank you.
very much. Thank you very much for coming to the session GA Swarm Intelligence. Don't forget, this is the first two were like best paper nominations. You can vote for them. You have to check your email box how to do that. Oh, yeah. Yeah, okay. Well, those are the only one you will find available, right, to vote on, so you cannot make a mistake. Actually, you can vote on any best paper nomination on the conference, right? It doesn't have to be this session, but you can only vote once. I mean, in the past, you could vote at each track, but that's eliminated. All right, within half an hour, the poster session will start in the patio. So, and afterwards we will have the buffet also there. So enjoy the evening.